Okay, let's get into it. Today we're doing a deep dive, really trying to get our heads around the Higgs boson and, maybe more importantly, the Higgs field. Our mission is to figure out how this field gives particles mass and maybe uncover a pretty big surprise about where your mass, the listener's mass, actually comes from.
Yeah, that's the kicker. But first things first, the Higgs field.
So, the basics. It's described as this invisible field everywhere in space and time, even in a vacuum. And crucially, it's a scalar field.
Scalar, yeah. That just means it has a magnitude, a strength, but no direction. Think temperature, not wind.
Okay.
But the really weird part, the key thing, is its baseline energy level, what physicists call the VEV, the vacuum expectation value.
And that's not zero.
Exactly, it's non-zero. Unlike other fields, its minimum energy state isn't empty. It has this background value. That's the anomaly that makes everything else possible.
And that's what gives particles mass, this non-zero floor. Minini used a pretty helpful analogy.
Last this one.
Yeah.
Yeah, it's useful. Think of the field like this thick, invisible liquid filling all of space.
Like cosmic treacle?
Sort of, yeah.
Yeah.
And as particles move through it, they interact. Some interact really strongly.
They feel a lot of drag, a lot of resistance.
Precisely. And that resistance, that inertia, is what we perceive as mass. The top quark, for instance, interacts heavily, so it's massive.
Whereas something like an electron interacts just a little bit.
So it's very light. And then you have particles like the photon, the light particle,
Zips right over it.
experiences zero resistance, zero interaction. So massless.
Got it.
Yeah,
And the strength of that interaction has a technical name.
it does. It's called the Yukawa coupling. That determines how sticky the molasses is for each specific particle type.
Okay, so that's the field, this pervasive molasses. What about the boson itself, the thing they found at CERN?
Right, the Higgs boson. That's actually a different thing. It's the particle associated with the field. Think of the field as the water in a pond.
And boson is like a ripple.
Exactly. In excitation, you need to pump energy into the field to create one, which is what the Large Hadron Collider does. It smashes particles together with huge energy.
And that discovery in 2012 by ATLS and CMS, that was the proof.
Huge moment. It confirmed the theory from way back in the 60s. And the boson they found has specific properties, right? Mass around 125 GeV.
Zero spin, which makes it scalar, like the field.
Right, no electric charge.
Yeah.
And it's incredibly unstable, decays almost instantly.
Okay. Now, you mentioned a surprise earlier
Yeah.
about where our mass comes from.
Yes. This is the really crucial takeaway, I think. The Higgs mechanism, this molasses thing we talked about, it works for elementary particles, quarks, electrons.
Not for us. Not for everyday matter.
Well, only indirectly. And only a tiny fraction. The mass the Higgs gives to the quarks and electrons inside your atoms. It accounts for only about 1% of the total mass of the protons and neutrons that make up almost everything.
1%.
Oh, yeah.
Seriously. So where's the other 99% coming from?
Energy. Pure energy. Remember Einstein's EMC-FCS?
Mass is energy.
Exactly. Almost all your mass comes from the kinetic energy of the quarks buzzing around inside protons and neutrons, and even more so from the binding energy of the strong nuclear force holding them together.
The gluon.
Yes, the energy in that gluon field, governed by QCD, quantum chromodynamics, were basically made of bound-up dynamic energy, far more than stuff given mass by the Higgs.
Stays genuinely mind-bending, so 99% is just energy holding things together.
Pretty much. It reframes how you think about matter, doesn't it?
It really does. Okay, one last piece then. How did the field get that weird non-zero value in the first place? You mentioned symmetry breaking.
Right. The sombrero potential analogy helps here. Imagine a sombrero hat. The very center point at the top is high energy, unstable. That's like the universe having a zero Higgs field value.
Okay.
But the universe wants the lowest energy state, so it rolled down from that unstable peak into the circular brim of the sombrero.
Which is lower energy.
Minimal energy, yes. But notice, in the brim, you're not at the center anymore. The field has a non-zero value. That fall is what we call spontaneous symmetry breaking. It separated the electromagnetic and weak forces and gave particles mass through the Higgs mechanism.
Wow. And this leads to a final, slightly unsettling thought.
Potentially, yes. Based on the measured mass of the Higgs boson and the top quark, the heaviest quark, our current vacuum state, the brim of the sombrero we live in, it might only be metastable.
Metastable meaning stable for now, but maybe not the most stable state possible.
Exactly. Like a ball resting in a small dip on a hillside, not quite at the bottom of the valley. There could be an even lower energy state, a true vacuum.
And if the universe somehow tunneled into that state,
Well, the laws of physics as we know them would fundamentally change the constants, the forces, everything. It would be a completely different universe.
Okay, that's a lot to think about. So, recap. Higgs gives maybe 1% of mass to fundamentals, 99% is nuclear energy, and the whole setup might not be permanent.
That's the essence of it. A pretty wild ride from a simple question about mass.
Definitely leaves you with something to ponder. Thanks for breaking that down.